Yeah, there we go.
Don't embarrass you. So you have to there by the
Perfect. Okay. And what time does it finish? 12:30. I think we'll be fine. I've been through it a few times. I was saying to Alex, if Heloise took this class, she should be able to pass it. She's heard it enough.
I'm glad it's not just me.
She wasn't listening, though.
My daughter keeps volunteering to make my slides more interesting.
I'm sure when...
More colors, some background.
That's funny. I'm sure when a show comes, he'll have memes in his slides. He always has memes in his slides. Yeah.
I've never heard either of you. I've heard you speak now from the back.
She explains really well.
Does he
fun-
say on the message?
No. The way to argue with a show is just to let him talk. I completely... Yeah, it's perfect, right? You know, you plant a seed, he disagrees with it. You just have to sit back, and then eventually comes around to it, and then you tune back in. Of course, you don't really tune out.
Let's get started. Good morning, everyone. We're going to get started. So it's a pleasure and an honor to introduce today's guest speaker. We have Rob Shakir here with us, and we really couldn't have found someone more perfect to lecture on this topic. So Rob is one of the key technical leads at Google's global networking team. This is the team that runs the entire wide area backbone network that Google operates. But he's also responsible with other folks in doing the technical evaluation of router equipment and deciding what Google runs in that wide area network backbone. He's also one of the lead authors on OpenConfig, which is pretty much becoming the de facto standard for how you configure and manage routers in the network. And also, sorry, that's a long list of achievements, one of the main authors on segment routing, which is probably the cutting edge in routing protocols that's for the IETF standard, which is, I think at this point, is standard, right?
Yeah.
Oh, right. So without any further delay, thanks, Rob, for being here, and welcome.
Thank you very much. I think it's funny. I really wish that at some point I'd done a computer science course and been taught about routers at all, but I'm going to talk about something that I've been working on for about 20 years, which is a large number to think about, and just kind of share, I think, some of the background and some of the information about things that I've spent a lot of my life thinking about, but other people might not know about or think that it's just a box in the corner of their apartment that deals with their broadband. So we'll start out, and I think you've seen this picture before. What's the purpose of an IP router? An IP router is there to be able to take a packet, figure out where it should go, and route it along the right link. So, in this case, a packet comes in with a specific destination address. It's got a specific link it needs to go down. And so we're going to talk about how does it actually do that? What's the, look at what a router does and talk a bit about, and I'm just going to disclaim this. I say router, I'm British. In America, they say router. I'm not going to try and say that. That's something that cuts grooves in wood in the UK. So I'll stick to the one that moves packets. So it's things that perform IPv4, IPv6 lookups against the destination IP of a packet. You'll remember or be talking about that they run routing protocols, which is how they learn about routes that are going to be, tell where things are, where to route towards. And routes are I also say route, not route. Again, British disclaimer. Routes are sets of destination IP addresses. So today we're going to talk about what is a router. And to start with, we're going to take a little bit of a step back. And this is, the things when we start talking about a router can often be quite dry and not really know how it fits into the real world. So these are a couple of photos I've taken, or I think maybe I took the one on the left and not the one on the right, sorry. And we'll talk about a little bit about what makes up the internet. The internet is really just a bunch of networks connected together. And what's connecting those networks together is routers. And when we deploy those routers, we put them into some facility, like these ones. They're buildings that are specialized to have the power, the cooling, and everything that we need to be able to put routers in there and interconnect with each other. So when Google interconnects with Comcast or Google interconnects with Verizon, that's in a building like this, most likely. And these buildings, if you go into them, it's just racks, floors and floors of air conditioning, racks that contain these routers that are what what we actually use to build the internet to kind of connect things together. And so here's a couple of photos. These are relatively historical photos because these are the ones that I can share. They're from a network that I worked on a few years ago. And this is what a router looks like. You know, we'll come back and kind of talk through what a router is, and we'll come back to one of these photos and have a look and say, okay, how does that map? And what is a router really? Well, it's just a computer that is really specialized for forwarding packets. And there's many different sizes of that router. You know, these are two different ones. You can see that one's got horizontal slots, the other one's got vertical slots. There's various reasons that they look a bit different, but really at the end of the day, that's what a router is. It's just a computer that we've designed to be really specialized to forward packets. And they come in different sizes. So, you know, you've got everything from the small blue thing here that might be a home router that's got Wi-Fi and it's got a small number of ports. We might have things that are one rack unit tall. That's the kind of unit that we use to measure things inside a cabinet. Is a rack unit. It's a couple of inches. And you'll see here that this one is a one rack unit. We might call it a pizza box because it looks like a pizza box. And then the larger case on the right-hand side of this slide is something larger that has more line cards. And the dimensions that we have in terms of these routers, we kind of measure, you know, the physical size. We also think about, well, how many ports does it have? You know, if the whole point of this thing is to forward packets and interconnect, then it really needs to have, you know, how many ports, how many times can I interconnect with other systems? And then the bandwidth. The bandwidth is how much capacity does this router have to actually forward packets? And obviously that's a really key thing. As we're looking at a certain data volume, we need to know, well, how much data can we put through a specific router? And so if we think about the definitions, you know, how we kind of talk about routers, we talk about them in these different dimensions. So, you know, we have the number of external ports that's there. There might be internal ports and things that are used to connect bits of the router together, but we don't think about those. We really think about the ports on the outside. And sometimes, you know, in the industry, they'll be called revenue ports because the vendors that you buy them from, they're the ports they can actually sell, they can actually charge you for. Then each port has some form of speed, has a speed of that port. We often refer to that as the line rate. So sometimes ports run at different speeds. You know, you could have a port that was 100 gigabit that was also able to run at 40 gigabit or also able to run at 10 gigabit. But these, when we're talking about the capacity of a router, then we think about what the line rate, what's the maximum rate of that port. And then there's the capacity of the router. So the capacity of the router is just the number of ports times by the speed of those ports. So if we think about this kind of small little router here that you might have at home, maybe it's got a couple of different types of ports. Maybe it has 400 megabit ports. That gives you 400 megabits of connectivity there. And then you might have one gigabit port. So that gives you a gigabit of capacity there. So the overall capacity is this 400 megabits plus a gigabit. So it's a 1.4 gigabit a second router. Probably can't actually do that because of how it's forwarding, but that would be the capacity of it. If we think about what we actually deploy in a network like Google's today, this is an 8-slot system. It has 8 line cards. We'll come on to what a line card actually is. Each one of those has 36 ports. So the number of ports here is 288. We have 36 times 8 ports. Each one of those ports can run at 400 gigabits per second. So the router capacity we have today is those 288 ports times the 400 gigabits, which is about 115.2 terabits per second, which is a lot more than your home router, but these numbers continue to get kind of interestingly bigger. And why do they get bigger? Well, you know, in this same size of physical deployment, we don't increase the number of ports. That's kind of limited by the amount of space we have on the front of the slot. You know, there's only so much physical space, and if we have to plug an optical module into it, there's only that much space for those ports. So it stays at 36 ports. We still have the 8 line cards. We didn't make the chassis any bigger or smaller. But we can then put different line cards, different modules into it, to rather than run at 400 gigabits per port, we can run at 800 gigabits per port. And that gives us a doubling of the capacity, of 288 times 800 gig now, and looking at about 230 terabits per second through this router. And these numbers change over time. So this is a view that we put together a few years ago in Google, which is now sufficiently old that I can share it. But if you see here, we started out with these systems on the left-hand side of the slide. The Juniper system there is 1.7 terabits per second. You know, then we got bigger routers. So the one along it was a physically larger. It had more line cards, which means it had more ports, which then increased the capacity. Same again, we increase the number of ports and the capacity goes up. But you'll see here that really at some point we run out of space. a rack is about 7 or 8 feet tall, depending on what exact size you have, and that's about the amount of physical space you get to put things in. There's then a physical size of optics, so that's how many ports you can get on each line card. But there's also some constraints around, like, well, how much power can I put into the rack? Some of these systems will be pulling 50 kilowatts of power. So there's a significant power draw. And you also, got all that power going in. Where's it going? A lot of it's going into heat, so you have to cool it. So a lot of the physical constraints that we have about how big a router, what the maximum capacity is going to be, is really around how much can we fit into that rack. And you'll see here that the numbers go up, but the things don't necessarily get much bigger. Even between this Cisco device, the ASR 9000 and the Arista 7500, the thing got smaller, but the capacity went up. And that's the result of when we increased the speed of the ports. So there we went from a 10 gigabit base system to a 100 gigabit base system. And as we go to 400 gigabit systems and 800 gigabit systems, as we kind of talked through on the previous slide, that's when we'll start, the capacity of the router continues to increase over time. Okay, so that's that kind of like the photos of what routers kind of look like. So let's talk about what actually is inside a router. So once we kind of peeled the metal skin off, what would we find? And we'll use this conceptual picture and we'll iterate on it a little bit to talk through what it does. So we have some chassis. That's the overall unit of router. It's the thing that collects all the line cards together. It's we would talk about a chassis having a capacity because the chassis is the overall router. That chassis has two different types of cards within it. It has a controller card, and then it has line cards. Controller cards are where the control processor, it's usually an x86 processor, probably running Linux, that sits in that device, and its job is to exchange routes with things, to do those control plane management plane software jobs, and program the line cards. The line cards themselves are the things that are dedicated to forwarding. So you've got the ports, the input and output ports on that line card. Input and output ports is the same set of ports. A port is bidirectional, and the same port can be the input and output port can be different ports on the same line card. It can be different on different line cards. The line card itself might have its own control plane processor, its own CPU, and that will be there to do anything that's local to the line card. Maybe it's managing whether links are up or down, or responding to any kind of local protocols that are running there. And then there's some way that we, once a packet's come in, we can interconnect to another line card. I'm kind of drawing it as a mesh here, where every port can talk to every other port. And then on the other side, we have more than one line card in the system. In some systems, or in the smaller ones, maybe they just have one. And then we have the output line card, which is doing the processing of packets before they're routed out into the rest of the network. And when we talk about routers, we kind of really talk about them in terms of planes. Like, that's the sets of functionality that the router implements. And so the first one of those is the data plane, sort of the real one that we care about, right? These are computers that we want to forward packets quickly. So really we care about, well, how is it forwarding packets? And that's made up of mainly the line cards. There's between 1 and 20 line cards in a system. Usually that's constrained by how big we can build the fabric, the thing that interconnects the line cards, and the physical size. At some point it's too difficult to fit. There's not enough space in that rack to fit more line cards in. And that helps you choose the capacity of a router. You can choose how many line cards the router might have. On a line card itself, you'll have some specialized hardware to forward packets. That's something that's designed really to do the packet forwarding. We'll go into a lot more detail about that. And then something that rather than having this full mesh of wires between every port, we want to have the line card is a removable unit. So we want to have something on the chip on the line card, on that thing that we can remove, that then packages the packets to be able to be transmitted to other line cards. And that thing that interconnects all the line cards we call the fabric of the router. So here we've got a fabric. There might be multiple fabric cards in a router that help that interconnection achieve the right bandwidth, help us have the right reliability. But then the forwarding chips and the fabric chips make up the data plane of the router, the thing that really that does the mean veg of the job and forwards packets. We then have the control plane. The control plane, I think, talked about a bit in terms of it gives you the way that you talk to other routers, the thing that runs the control protocols, the routing protocols, to be able to talk to other routers and figure out what routes to have. So it might be running BGP or an IGP like OSPF or ISIS, and it then exchanges those routes. It figures out what the routes we want to use are, And it's then responsible for disseminating those routes down to the line cards. So the line cards themselves don't really know any